We'll now start a very important chapter. So this is called Hilbert spaces. So Banach spaces and Hilbert spaces dominate functional analysis. A Hilbert space is a Banach space with some geometry built in. In particular, we say when two vectors are orthogonal to each other or at right angles to each other. So we introduce the notion of an angle. How is it done in R2? For instance, if you take the plane R2 and you have two vectors x equals x1, x2, y equals y1, y2, then mod x is the norm x2, that is the norm in ln2. So you think of ln2, L22 for instance. Okay, so this is the norm x2, and then you have what you have what is called the inner product x dot y equals mod x mod y cos theta. So that you say two vectors are orthogonal to each other if theta is the angle between them. And if that is cos pi by 2 is 0, so if x dot y is 0, we say the two vectors are orthogonal. And this can also be written as sigma x1 y1 plus x2 y2. Okay. And we have that x dot x is mod x square, that is the inner product generates the norm, and it is linear in each of the variables. It is linear in x, it is linear in y. Okay, so we generalize all these things and define an inner product. So definition: let V be a real norm-linear space. An inner product on V is a form from V cross V into R such that one, it is symmetric. That is, for every xy in V, you have xy equals yx. Okay, and then 2, it is bilinear. Therefore, that means alpha x plus beta y inner product z will be equal to alpha xz plus beta yz. This is for all x, y, z in V and for all alpha, beta in R. So it's also linear in the second variable because you can interchange by symmetry. It also means that it is linear in the second variable. And then thirdly, you have that xx equals norm x square. Okay, so such a bilinear form is called an inner product. So now what happens if you have a complex? So if V is over C, then 1 becomes xy equals yx is nothing but xy conjugate. Okay, it is linear in the first variable, and therefore this means we have x alpha y plus beta z will then become alpha conjugate xy plus beta conjugate yz. So this is called, and it's linear in the first variable, it is conjugate linear in the second variable, and such a form is called a sesquilinear form. Okay, so that is, these are the changes you have to make when you are dealing with complex. Okay, so definition, Hilbert space is a complete inner product space. That is, it is a Banach space whose norm is generated by an inner product. Okay, so now time for examples. So we have Rn with the norm 2. This is the space Ln2, for instance. So you define the inner product xy equals sigma I equals 1 to n xi yi. Okay, and then if you take Cn with norm 2, then you define xy equals sigma xi yi bar. Okay, so this is obviously the inner product because you have xx equals norm x square and the other properties are immediate to verify. So then example 2, little l2, again if you have x equals xi, y equals yi, then if L2 is over R, then you define the inner product as sigma I equals 1 to infinity xi yi, and this is well defined, this is convergent because by Hilbert's inequality this is less than or equal to norm x times norm y, and therefore this is well defined. And then if you have L2 over C, if you have complex numbers, then you define xy as sigma I equals 1 to infinity xi yi bar. Okay, so these are the examples for this. Then example 3 is L2 of mu. So if you have xs mu is a measure space, then L2 of mu is Hilbert space. Well, it's complete, and now the inner product, you can easily guess, is nothing but integral fg d mu in the real case, and in the complex. So this is, if the base field is R, then you have this. If the base field is C, you have fg equals integral over x f g bar d mu. Okay, so this gives you Hilbert spaces. Okay, so now I will mostly deal with the reals. Wherever complex needs to be mentioned, I will tell you what is the change to make. Okay, so now my x plus y square is what? X plus y. So you use the linearity and develop this, so you will get xx, which is norm x square, plus xy, and then you will get yx, so that is 2 times xy plus norm y square. So in the case of complex, so complex case, you have norm x square plus xy plus yx is xy bar, so 2 real part of xy. So this is the real, this is a complex number, so you have this plus norm y square. Okay, so that is the thing you have in the complex case. Okay, so now if I similarly write x minus y square, so this is equal to norm x square minus 2xy or 2 real part of xy plus norm y square. And so if you add these two, you get norm of x plus y by 2 whole square plus norm of x minus y by 2 whole square is 1/2 of norm x square plus norm y square. So this is what is called the parallelogram, parallel identity. And this is what in two dimension, in the plane I called as Apollonius Theorem, and we have seen this. Okay. So remark, a theorem of Frechet, Jordan and von Neumann states that a Banach space where the parallelogram law identity is valid is in fact a Hilbert space. That means you can write down an inner product which generates a norm. Once you have the parallelogram identity, you can use it to do it. So example, you take C01, this is a Banach space with the sup norm, and cannot be made into a Hilbert space. That means the parallelogram law will fail. So you define ux, so you take not C01, let us take minus 1 1. You can do it with C01, but it's easier to write it with C minus 1 1. So this is equal to minimum of x and 0. So that means, how does the graph of u of x look like? When x is negative, you take the value, and then when x becomes positive, then it is. So this is the function u, and then v of x is x itself, so this is v. So u goes like this and v goes like this. Okay, so these are the two functions u and v. Then norm u equals norm v equal to 1, as you can easily see. So this is minus 1, this is 1. Okay, and norm of u plus v by 2, in this part it is, both of them are the same, so you will get 1, and then so infinity. All these are the L infinity norms, and norm of u minus v by 2 will only be half, because here it will be u minus v is 0, and here it is half of x, and therefore u minus v by 2 will be half, and you will say that the parallelogram law fails for this pair of functions. Okay. Theorem H. Hilbert. H is uniformly convex, and so hence it is reflexive. Okay, so proof. So you have norm x less than or equal to 1, norm y less than or equal to 1, norm of x minus y greater than epsilon, Then from the parallelogram law, you will get norm of x plus y by 2 is less than or equal to 1 minus epsilon square over 4, and therefore this can be written as square here, 1 minus delta square for suitable epsilon, and therefore you have uniform convexity, and we know that every uniformly convex space is reflexive. Okay, so every Hilbert space is reflexive. Okay, now when we wrote the Hilbert's inequality, when P equals 2, which is equal to P star, I said Hilbert is Cauchy-Schwarz. And what does it mean? It is sigma, or if in the notation which I wrote earlier, xy inner product is the same to norm x2 norm y2. Okay, so this is a Hilbert inequality applied to P equal to P star equal to 2, and xy is nothing but sigma xi yi. I equals 1 to n, I equals 1 to infinity, whatever space you are working with. Okay, so this is in fact a fundamental property of Hilbert spaces. So we have the following theorem: Cauchy-Schwarz inequality. So H is a Hilbert space and xy in H. Okay, then mod of xy. So this is a very fundamental inequality which will be used again and again and again. So norm x times norm y. Okay, equality occurs if and only if x and y are scalar multiples, x and y are scalar multiples of each other. Okay, so proof. So we will do it for the complex case. The real case will be a particular case of that. So let us assume, so theta in C such that you have mod theta equal to 1 and theta times xy is mod xy. We have done this before. In some various examples we have done this. Given a complex number, it can be written as r times e power I theta. So theta e power I theta I am calling theta now, and so any complex number can be written as a number with modulus 1 times its. So I am bringing that down here. So you have this number here. Okay, so if t is in R, we have 0 less than or equal to norm of theta x minus ty whole square. So let us expand this. This will give you norm theta x whole square, that is norm theta square norm x square. Theta has modulus 1, so that will give you norm x square minus 2 times t is a real number, real part of theta x comma y plus t square norm y square. Now what is real part of theta xy? Okay, so theta x comma y is theta times xy, which is mod xy. Okay, so that's equal to, so it's a real number anyway, so that's equal to norm x square minus 2t mod xy plus t square norm y square, and that is always greater or equal to 0. So you have a quadratic polynomial which is non-negative, which is of constant sign. That means it should have, so you are having a parabola which never changes sign. That means it doesn't have any real roots. That means its roots are imaginary. So this implies, so this is true for all t in R, and therefore you have that the roots of this quadratic should be imaginary. So b square must be less than equal to 4ac. That means 4 times mod xy square is less than equal to 4 times norm x square times norm y square, and that implies that mod xy is less than equal to norm x norm y. So that proves the Cauchy-Schwarz inequality, which is a fundamental inequality, as I said. Okay, so if you want equality in this, so you should have that the roots should be equal. That means theta x should be equal to ty. Okay, and only then where t is a root of this quadratic polynomial, and therefore some t naught, and that proves whatever we wanted to prove. Okay, because you want equality means this is equal to 0 only then, so that means t must be a root of this thing, and it should be a perfect square, and therefore you have theta x equals t naught of y. Okay, so corollary, H Hilbert and y in H. Okay, so define fy of x equals xy for all x in H. Now this I am writing in this fashion with y in the second coordinate, so that it is linear in the first coordinate, and therefore even in the complex case or real case, it doesn't matter which, this is always a linear functional. Okay, and therefore mod fy of x by the Cauchy-Schwarz inequality is mod xy, and therefore that's equal to norm x into norm y. Therefore fy belongs to H star, and norm of fy is less than or equal to norm y. So assume that y is not equal to 0, and you take x equals y by norm y. So norm x equal to 1, and fy of x is xy, so that is y norm y by norm y, which is equal to norm y square by norm y, which is equal to norm y. So the maximum is reached on the unit sphere, and therefore so this implies that norm fy equal to norm y. Okay, so I didn't state the thing. Okay, so this is the proof. Let me state the theorem. So then fy belongs to H star, and norm fy equals norm y. Okay, so that was the corollary, and I have already proved it. Okay, fine. So we will see in the next chapter that every continuous linear functional in fact arises in this fashion. So H is isometrically isomorphic to its own dual, and so very often, especially in the real case, we can identify the two. Okay, so then another corollary, H Hilbert, let xn weakly converge to x and yn converge to y, then xn yn converges to xy. So when you have an inner product and one term converges weakly and one term converges strongly, then the limit is the natural whatever you expect. Okay, so if both of them are weak, then you cannot expect, like for instance in LP spaces also we saw an example, cos nt went weakly to 0 but cos square nt went weakly to half. So you cannot expect normally when you are dealing with the product of a weak convergence to behave properly. You don't know what will happen, but if one is weak and one is strong, then you are on safe ground. Okay, so proof. Okay, so mod of x and yn minus xy is equal to less than or equal to mod of xn yn minus y plus mod of xn minus x y. Now the first one by Cauchy-Schwarz inequality is less than or equal to norm xn norm yn minus y plus fy mod xn minus x. And now every weakly convergent sequence is bounded, so this is less than or equal to m times norm yn minus y plus mod fy xn minus x, and then both of them go to 0. The first one goes to 0 because yn converges to y strongly, and this goes to 0 because xn converges to x weakly, and therefore x and yn converges to xy. Now, so in particular, if xn goes to x and yn goes to y, both of them are strong, then x and yn will also go to xy. That's now obvious that you could have done it in many directly, but now you know if it converges strong in norm, then it converges weakly, so xn goes to x weakly as well, and yn goes to y in norm, and therefore you have this. So okay, so that